Hello everyone. The second class of special lecture on biopolymer chemistry begins. Today, I would like to talk about the mechanism of an infrared spectrophotometer, a device that measures infrared absorption spectra. Infrared spectrophotometers can be roughly divided into dispersion type and Fourier transform type. In both spectrophotometers, the light from the light source is detected by the detector. It measures how much of the light emitted from the light source is absorbed by the sample. In the dispersion type, infrared light is dispersed using an optical element called a diffraction grating. Since the angle reflected by the diffraction grating varies depending on the wave number of infrared light, the light reflected at a specific angle is detected by a detector and the intensity of infrared light at that wave number is measured. A spectrum can be obtained by continuously measuring another wave number while changing the angle of the diffraction grating. On the other hand, the Fourier transform type measures the spectrum by a completely different principle. All the light from the light source is introduced into an optical element called an interferometer without being divided by wave number. Then, the intensity of the interfered light is measured with a detector. There are three mirrors in the interferometer, called the beam splitter, fixed mirror, and moving mirror. The intensity of the interfering light caused by the optical path difference between the fixed mirror and the moving mirror is detected by the detector, and the spectrum is obtained by Fourier transforming it. In this way, the dispersion type and the Fourier transform type measure spectra with completely different methods. At present, almost all infrared spectrophotometers are of Fourier transform type called FTIR, and dispersion type is rarely used. First, I will explain the light source used in the infrared spectrophotometer. It is desirable that it shows a continuous emission spectrum in the infrared region, has stable light intensity, has heat resistance, and has a long life. All substances emit electromagnetic waves according to temperature. When an illuminant can be approximated with a black body, its spectral radiance is given by this equation as a function of wavelength and temperature. This figure shows how the emission spectrum changes when the temperature is changed. The horizontal axis is the wavelength, and the region shown in rainbow color is the visible light and the region shown in red is the infrared light. For example, the surface of the Sun is about 6000 Kelvin, so you can see that strong visible light is emitted. Almost no visible light is emitted from light sources below 600 Kelvin. Since the efficiency of the infrared light source is high if the intensity of the part shown in red is high, the light source heated from 1000 Kelvin to 2000 Kelvin is used in the infrared spectrophotometer. In practice, a Glover light source made of silicon carbide and an Ernst light source, which is a ceramic containing zirconium oxide as the main component, are used. Each is heated to an appropriate temperature and used as a light source. Infrared detectors are roughly divided into pyroelectric effect type and photoelectric effect type. Pyroelectric effect detectors electrically detect changes in surface charge in response to changes in temperature due to light absorption. This type of detector is wavelength independent in sensitivity, requires no cooling and can be used at room temperature. However, since light is once converted into heat, the response speed is slow and the sensitivity is not very high. A detector that uses a crystal of triglycinous sulfate, abbreviated as TGS, or its deuterated compound, DTGS, as a pyroelectric element is used. On the other hand, the photoelectric effect type detector uses the photoelectric effect, which is a phenomenon in which electrons are excited from the valence band to the conduction band and a current flows when a semiconductor is irradiated with an electromagnetic wave having energy higher than the band gap. In principle, it is the same as solar cells and silicon photodiodes. Silicon is excited by light with a shorter wavelength than visible light, but it is not excited by infrared light because it has lower energy than the band gap. To be used as an infrared light detector, it must be excited by infrared light. Therefore, for the detection of mid-infrared, a semiconductor with a narrow band gap called cadmium mercury telluride, or MCT for short, is used. Indium gallium arsenide is used for near-infrared detection. In either case, since the band gap is narrow, electrons may be thermally excited at room temperature, which causes noise. Therefore, it is necessary to cool with liquid nitrogen before use. Since the MCT detector has higher sensitivity than the pyroelectric effect type, it is often used for measurement with low light intensity such as infrared microscope. It is also used to track fast reactions because it has a fast response. The sensitivity of the detection element is evaluated by the value of the specific detection capacity d star. This value is expressed as the value of the signal-to-noise ratio for a 1 watt optical input, with higher values indicating higher sensitivity. The signal-to-noise ratio is the ratio of the intensity of randomly generated noise to the intensity of the signal you are trying to measure. Since the signal is used as the numerator and the noise is used as the denominator, the higher the value, the higher the signal intensity and the better the sensitivity. D star can be obtained by using this formula to normalize the detector area, incident energy, noise bandwidth, etc. This figure shows the spectral sensitivity characteristics of various infrared light detection elements. The horizontal axis shows the wavelength and the vertical axis shows the specific detection capacity d star. The straight line shown at the bottom of the figure is a pyroelectric type detector, which has low sensitivity overall, but has no wavelength dependence of sensitivity and can detect a very wide range. MCT detectors are more sensitive than that. There are narrow band, medium band, and wide band MCT in which the band gap and detection range are changed by adjusting the mixing ratio of mercury, cadmium, and tellurium. The MCT that can detect a wide range has relatively low sensitivity, and the one that can detect only a narrow range has a high sensitivity. This figure shows the wavelength dependence of the transmittance of various optical materials. Wavelength is used on the horizontal axis and transmittance is used on the vertical axis, and the ultraviolet, visible, near, and infrared ranges are shown below the horizontal axis. For use inside an infrared spectrophotometer, it must have high transmittance in the infrared region. Often used is potassium bromide, KBr, shown in broken lines in this figure. It transmits a very wide range of light from the mid-infrared region to the visible/ultraviolet region with high transmittance. However, since KBr has high hygroscopicity, the material called KRS5 is used as a substitute in order to avoid deterioration due to moisture absorption. KRS5 has a lower transmittance than KBr as a whole, and transmits light in the infrared region well, but does not transmit part of visible light. An example of the optical system of a dispersive infrared spectrophotometer is shown below. Normally, the dispersive spectrophotometer is of double beam type, and the light emitted from the light source is divided into two. A sample is not placed in one of the optical paths, and it is a reference light that directly measures the intensity of light from the light source. The reference light is reflected by the mirror M6 and reaches the rotating sector mirror M7. The sector mirror has a part with a mirror and a part without a mirror, and alternately enters the optical path by rotation. Light passes through to the detector when the part without the mirror enters the optical path of the reference light. The light is reflected by mirrors M8 and M9, passes through the entrance slit, is collimated by collimator mirror M11, and is then dispersed by the diffraction grating. The light reflected by the diffraction grating is focused again by the collimator mirror M11 and passes through the exit slit. Then, it is collected by the elliptical mirror M15 and detected by the detector. On the other hand, when the light beam on the sample side passes, part of the light is absorbed and weakened by the sample. Then, the part of the sector mirror M7 with the mirror is reflected when it is in the optical path, and goes toward the detector. It is reflected by the diffraction grating through the same path as before, and is detected by the detector through the exit slit. In such a double beam spectrophotometer, the reference light and the sample light are alternately detected by the detector in synchronization with the rotation of the sector mirror. Therefore, the time change of intensity is as shown in the upper right figure. The intensity of the reference beam is high and the intensity of the sample beam is low. The transmittance can be calculated from this intensity ratio. This is the inside of an actual double beam type dispersive infrared spectrophotometer. The light source is on the right of the figure, the sector mirror is in the center, the diffraction grating is on it, and the detector is on the upper left. It differs slightly from the optical layout of the spectrophotometer shown on the previous slide. The light emitted from the light source passes through the optical path of the reference light, is reflected by the sector mirror, is reflected by the collimator mirror, is dispersed by the diffraction grating, passes through the slit, and is detected by the detector. This slide shows the optical path of light through the sample. Part of the light from the light source is absorbed by the sample, passes through the sector mirror, passes through the entrance slit, is reflected by the collimator mirror, is dispersed by the diffraction grating, passes through the exit slit, and is detected by the detector. Will be done by changing the angle of the diffraction grating. Light with different wave numbers enters the detector. Next, I will explain the diffraction grating. As shown in the figure on the lower left, the diffraction grating has a structure in which fine lines are engraved at equal intervals on a flat plate substrate. The diffraction grating shown here has lines engraved in the vertical direction. When white light with various wavelengths is incident on it, the reflection angle changes depending on the wavelength, and the reflected light appears rainbow-colored. The figure above shows the cross-section of a diffraction grating, which has a sawtooth cross-section. There is an optical path difference between the light reflected by G1 and the light reflected by G2, causing interference. The optical path difference between the incident light I1 and the incident light I2 is equivalent to the length of the line segment shown in red, and is d sin alpha, where alpha is the incident angle and d is the lattice constant, that is the interval between the engraved lines. The optical path difference between the reflected light O1 and the reflected light O2 corresponds to the length of the line segment shown in blue, and is d sin beta when the reflection angle is beta. Together, the optical path difference between the light reflected by G1 and G2 is d sin alpha sin beta. If this is an integral multiple of the wavelength, the reflected lights will strengthen each other, so the light of wavelength lambda that satisfies the relational expression on the right will be strongly observed at that angle beta, where m is an integer and is called the interference order. Actually, when white light is incident at the angle as shown in the lower right figure, the white light that includes all wavelengths of the incident light is reflected at the angle called 0th order light. As the interference order m changes from -3 to 3, the -3 RD, -2 ND, -1 ST, 0th, +1 ST, +2 ND, and +3 RD order light is reflected in order from the right. Then, light of long wavelength to short wavelength is reflected from the side closer to the 0th order light to the side farther from it. At the angles shown in gray in the figure, the first order short wave light and the second order long wave light overlap. Therefore, it is necessary to use an optical filter to remove secondary light in this area. When using a diffraction grating in a spectrophotometer, the +1 st order light or -1 st order light is usually used for measurement.